Thanks everyone for joining this Datadog On episode. Datadog is a series of events where we invite engineers, designers, product managers working every day on building Datadog itself to tell us about a project, a piece of technology, a language, anything that can be interesting on how we're building Datadog on a daily basis. Today, we are going to be talking about how we build our event storage system. So a couple of things, a couple of housekeeping items. This episode will be recorded and it will be published on YouTube and also on our website, where you can find every other episode that we ever done. So if you go to our website, datadogon.datadoghq.com, you can not only watch this one once it's available, but also watch any of the previous episodes. Also, we are going to leave enough time at the very end for Q&A. We love these episodes to be very interactive. The idea is not only to show things that we've built, but also to have a conversation afterwards with the attendees. So if you have any questions throughout the episode, feel free to use the Q&A button on your Zoom client and post your question. There is also a chat window. Feel free to use the chat window to say hello, to say where you are, to discuss with other attendees throughout the event. But again, if you have questions that you want the speakers to answer, just use that Q&A button so we can basically know exactly where the questions are, and we don't have to read everything else on the chat window. Good. So let's get started. Before getting started, we usually do a little bit of overview of Datadog. Many of you already know what Datadog is, but the idea of these events is that we explain how Datadog is built, not Datadog itself. So just so you know, in case you don't know Datadog yet, Datadog is a monitoring and security platform that helps companies improve the observability and the security of their infra and applications. And my name is Ara Pulido. I'm one of the co-hosts and co-organizers of this series of events. So if you have any questions, any feedback, or a topic that you want us to cover in future episodes, feel free to reach out through Twitter or directly on my email address, and I'll be happy to answer any questions that you may have, or welcome those proposed topics that you want us to discuss. But the important people today are Guillaume and Ryan, of course. Guillaume, do you want to introduce yourself?
Yeah, sure. So hello, Ara. Hello, everyone. So I'm a senior software engineer here at Datadog from France. So I joined Datadog like 3 years ago. And since then, I have worked on Husky, which is the new event storage system that we are going to talk about today.
And Ryan?
Hello, everyone. I'm also a senior software engineer here at Datadog. I've been working on Husky with Guillaume for the same amount of time. I'm based in the US in Chicago.
Good. Welcome both. Thanks for joining us. So another thing that we usually do at the beginning of these episodes is talking briefly about Datadog Scale. And the reason why we do this is because some of the problems that we have, and also some of the solutions that we provide, make sense because of the type of problem that we are solving and the scale that we are operating in. So just to give you a little bit of overview, Datadog has more than 22,000 customers, and we are obviously a monitoring company, so we are gathering telemetry data from those customers, and that adds up to millions of hosts that we gather data from. That translates into tens of trillions of data points per day that we need to process, first ingest and then process. And obviously, this part of ingesting and processing telemetry data is one of the important bits that we are going to be discussing today. And one of the reasons why Datadog built this event storage system lately, because this is a quite new project, is one of the reasons is because Datadog is being around for about 12 years. And for a lot of that time, Datadog was mostly focused on infrastructure metrics. But in 2017, they decided to create also a logs product. And one of the reasons why suddenly the way we ingested and analyzed that it was different is because metrics and logs has some similarities but also some big differences. And Guillaume is going to explain those so you can understand the problem statement.
Yeah, so maybe let's start with common points between logs and metrics. So whether we query logs or metrics, we always query them based on a time range. So basically both would include timestamps. They also both have a set of tags like host or service. And usually these tags have a fairly low cardinality in terms of distinct values. And these tags are mostly used for filtering data. So like get me the metrics or the logs for host X, or they can also be used for aggregations. Like I want to group results by service, for example. So that's for the common point, but there are also important differences. So first, metrics have a single value, and this value is basically the main data that we are interested in when we query a metric. We want to know the average value over time, for example, or we want to know the P95 of this value over some period of time. So like if we build a metric data store, we can usually take advantage of this by pre-computing these aggregations and only store the pre-aggregated data. But on the other hand, if we look at a log, usually a log has some textual content and like many different attributes. So like here in this example, we see like a customer ID, a customer email, there could be like plenty of other attributes. And we may want to like filter on all these attributes, aggregate on all of them, and of course, like return their values. So let's have a look at the important characteristic of logs. So these attributes that I mentioned, they can have a very high cardinality. We are talking about fields like customer ID or transaction ID, and these fields would be like impractical to emit as a metric tag, for example. They also usually contain a high number of custom fields, which are sometimes nested. And basically that translates into a very high number of attributes. And remember that users, they want to be able to run queries on any of these attributes. So for a logs data store, basically pre-aggregation is not really an option. Users want to aggregate over many different attributes, not just a single value. So it's not practical or it wouldn't be practical to pre-aggregate over thousands of different custom fields. I mean, we could not do that. Also, users, they want to, when they investigate incidents, for example, they want to list and retrieve the individual logs. So obviously a logs data store has to keep every single event. So one important thing in these first couple of slides, I talked about logs, but internally we prefer to use the term event. And that's because there are different products at Datadog which use the same event storage system. And log management is one of them, but there are other products like APM, application performance monitoring, or network performance monitoring are different products from logs, and they all use internally the event storage system.
Makes sense. Thanks for the explanation, which brings us to the first generation architecture of the event storage system, because the solution that we are presenting here today is not the first one that we had at Datadog. It's been more of an evolution as we learned about that problem space. So Guillaume, what was how was it like, the first system that we had?
So this first system, first generation, as we call it, was very simplistic. So basically the system was split into multiple cells, and each cell was running its own search cluster. And by having multiple cells, basically, we could have search clusters or keep the search clusters like reasonably small, or at least with a manageable size. And then each tenant, so each customer, was assigned to a single cell, which is good for isolation. I mean, if we have a problem with a search cluster, it only impacted the customers in this cell. But the main problem that we had was that if we had a single misbehaving node in a search cluster, that could disrupt the experience of all the tenants in the cell. Queries could become slow, they could fail entirely, or ingestion could block. So yeah, obviously that was not really good. And yeah, there were also many different type of or many different challenges that we have with this first generation architectures. And one of them is that our customers, occasionally they see a traffic spike and they can send 10 times or 100 of times their baseline volume of event in a very short period of time. And in this case, they rely on us to handle those bursts. But sometimes with this architecture, to keep the search cluster alive when we were seeing those traffic spikes, that sometimes required a lot of manual operations and babysitting. So basically, we started working on a brand new system, which we end up calling Husky. But before that, and as the work on Husky was going to take some time, we introduced a second generation architecture to give us some breathing room.
Good. So spoiler alert, this system that we will talk about is called Husky, at least internally. So how long did this first generation system last? So it feels like it was too much toil to maintain. So how long did it last?
We had to support that for about 3 years, I would say, from when logs management went GA, which was in 2018. And we started the rollout of the second generation architecture end of 2020, beginning of 2021, basically. Oh yeah, 3 years, 3 good years.
Good. So that brings us to the second generation, that system that gave your team some breathing room while you were building Husky. So Ryan, can you tell us how this second system solved some of the issues that the first system had?
So in the second generation architecture, we manage clustering now ourselves. Each replica is a cluster of one, so none of the individual nodes know about each other. So this means that if a single misbehaving node can only ever disrupt as many tenants as shards we've assigned to that node. There's no way for that node to cause some type of cascading failure to the rest of the cluster. We introduced a new service called Shard Router that reads data from Kafka and writes it back to a new Kafka cluster. But this time we've reorganized the data into shards, which are just groups of Kafka partitions. And we automatically split tenants into the appropriate number of shards based on their data volume in the last 5 minutes. So we assign 2 storage replicas to each shard, and they only consume events from those shards' relevant partitions. On top, we added a custom query engine that knows how to query all of the tenants' data spread across the shards. And that custom query engine also merges the partial results together and generates the final query result.
So this second generation, I think, was okay to reduce some of the toil, but I guess as Datadog grew and new features were requested, that started requiring new solutions. Ryan?
Yeah, just keeping up with growth occupied a lot of the team's time during 2020. But product teams also asked for a lot of new features. The biggest one I would say was the ability to filter and aggregate on any event attribute without first creating a facet, but there were a few others. They also wanted a cost-effective solution for long-term retention and the ability to ingest late arriving data. And one product team even wanted the ability to store and re-aggregate DD sketches, which are Datadog's approximate quantile sketch, directly inside the event platform. So basically the ability to store pre-aggregated data inside the event platform. I'm only today going to talk about filtering and aggregating on all event attributes, but those are also definitely some other interesting challenges. So what was the main problem with filtering and aggregating on any event attribute? In the legacy system, filtering and aggregating on an attribute required expensive upfront indexing. Even if we could go back after the fact and add a facet for existing data, it wouldn't be instant. We did end up shipping a solution for filtering with any field on the legacy system, but it was a lot of work and it didn't work for aggregation. The reason that it didn't work for aggregation is that we basically just jammed all of the unfaceted fields into one internally hidden text field so that when you would search for it, we could find it in that big hidden field, but that obviously wouldn't work for aggregation because it's just one big string mashed together.
Good. I'm sure that if there are any customers of Datadog watching now, that have been using Datadog for a while, they remember that need of creating that facet and not being able to search for previous to that facet log. So I'm guessing there are some excitement building up here, which bring us to third generation, which, as Guillaume said, is called Husky. And Guillaume actually is going to give us an overview of the architecture. So people understand, as we've seen, how the architecture of the first system was, how the architecture of the second system and the differences. Now we are going to show how this third system looks like so people can compare to each other.
Yeah. So the big difference between the second generation architecture and Husky is that Husky architecture separates compute from storage. So this is like fairly common technique today. And the idea is to be able to scale these components independently. So basically, if the amount of data stored increases, we want to scale storage. And on the other hand, if the query load increases, if there are more queries, we want to scale the compute resources. So that's one thing. The second thing is that Husky uses columnar storage. So we saw earlier that events can contain like hundreds of different attributes. And basically by being able to fetch data for only the specific columns we're interested in, we make sure to only use the minimum amount of data we need to process the queries. So Husky doesn't fetch data for columns which are not accessed at query time. One important thing is that the Husky query engine uses vectorized processing. So what that means is that instead of processing queries row by row, basically Husky runs operation column by column. And yeah, it processes like an entire column in a single step. So like column data is stored contiguously in memory, and we call that a vector. And then we have like tie loops, which run operations on each vector element. And that makes a very efficient utilization of the CPU caches. And that improves queries performances dramatically. So like this is a basic diagram of the Husky architecture. So it's a bit complicated. So what I'm going to do is explain the different blocks that we see in this picture. All right, so let's start by the core of Husky, which is composed of these two different types of storage. First, on the right side of this block, we see the blob storage. So the blob storage that depends on the cloud provider. That could be S3 if you're on AWS, but that could also be like Google Cloud Storage or Azure Blob Storage on other cloud providers. And the blob storage is where we store the actual column data. And basically, we put the data into files, and files contain contain column data for basically thousands to millions of individual events. And then on the left side, we see the metadata store. And the metadata store is based on FoundationDB. And here we store basically metadata elements. So there is a one-one relationship between the file and the metadata element. And the metadata element basically contains the location of the file on the blob storage, along with the time range of the events which are in that file. There are also a bunch of other information that we store in this metadata element, and we'll come back on that later in the talk. Then these metadata elements, it's important, they are indexed by time. And the reason we do that is to be able to easily find the files matching a given time range, because that's the first step that we have to run when we execute a query. So now, let's have a look at how data is ingested into Husky. So we have this component, which we call the writers. And the writers, what they do is that they read events from Kafka buffers, from Kafka topics. They buffer these events in memory for a short period of time, like typically a dozen of seconds. And then they organize like the buffered event into columns, and they write these columns into our custom file format. Then once we have created a file with all the columns, we upload these files to blob storage. And finally, the writer commit the presence of new files into the metadata store. And once this is done, the events, they immediately become visible for queries. So one thing to realize here is that writer nodes are completely stateless, and they can basically auto-scale based on the amount of traffic to ingest. And the important thing is that we never communicate with writers at query time. So basically, queries, they can't break ingestion, and vice versa. Problems on query side cannot break the ingestion. So I mentioned queries, but before talking about queries, we have to talk about compaction. So the files which are generated by the writers, they are relatively small because we cannot buffer events for too long because we want to make these events like visible quickly for queries. So the files are quite small. And basically if we want to query this scattered data, it's not super efficient. So what we use is compactor processes, like in the background. They look at the small files and they basically merge small files together into larger ones. And these compacted files, they are then uploaded to blob storage. And at the end, the compactors commit this outcome into the metadata store. So basically, the compactor will say, okay, I took these n small files, so now consider them as deleted, they don't exist anymore. And instead, I generated this large compacted file. So now queries should see the compacted files and not the small files that have been merged together. And this commit operation, it's an atomic transaction in FoundationDB. So basically queries, they never get an inconsistent view of the data. Either they see the small files which were merged together, or either they see the large compacted file. So like everything else in Husky, the compactor service auto-scales. So there is some like a mechanism to make sure that basically there are several compactor instances. So we don't want them to like try compacting the same files because that will not be super efficient. So what they do is that they elect a leader node which plans the work and then distributes it to worker nodes. And yeah, the compaction is quite important to improve query performance. And we'll come back to that later in the presentation, and Ryan will talk about that a bit more. So meanwhile, let's continue our journey through the diagram here. And what I want to talk now is the query side. So basically, we have these pools of reader nodes, which are the leaf nodes in Husky, and they run queries over individual files, which are fetched from the blob storage. So the readers, they return like partial aggregates, which are then re-aggregated by the distributed query engine. And these readers, they are also stateless or almost stateless. I mean, we could, I won't explain into details why it's almost stateless, but maybe we'll come back to that if there are questions. But basically, the idea is that they can be scaled up or down based on the query load. So it's important to note here that there is no relationship between a customer's data volume and how much hardware we can throw at their queries. Like even if a customer's data volume is tiny, we can allow like a query targeting the full retention to temporarily burst into a very large number of reader nodes. If we have the spare capacity, it's possible. So yeah, let's have a look a bit more in details at this point because it's important. So like when we run queries into the legacy system, basically customers they are allocated resources in proportion of the amount of data they ingest. So here in this example, we have three customers, like a large tenant, a medium tenant, and a small one. And what we see is that the resources for each tenant on query side are allocated based on the tenant size. So if we have a small customer, it can only use the allocated resources. And if it tries to run like a heavy query, for example, a query targeting the full retention, then it's probably going to put a lot of load on this node, and the query would likely be slow or fail entirely. And the problem is that this could also negatively impact like other customers which share the same query node than this one. So if we look at Husky on the other hand, on Husky there is just one like big query pool, and all tenants can use the full capacity of the pool. So like basically, the customers can use the resource of the pool like independently of the amount of data they ingested. So if a cluster is idle, like a small customer can burst and use like all the resources for their full retention queries. Like most of the time, unfortunately, clusters are not idle because they usually run like lots of concurrent requests, which can be like either simple or complex, and from many customers, like small or large. And what we try to do in Husky is to give a nice user experience out of all these different type of queries which run into the system. So Husky implements like end-to-end quality of service. And what that means is that we ensure that small queries, they see consistently low latency, and like big queries, they can eventually finish.
Good. Makes a lot of sense. Did it happen with the legacy system a lot? That use case that you mentioned of a small tenant doing very large query because they want to know a lot of data from all the retention period and slowing down all the customers? It's
actually very common for customers to like suddenly triggers like many complex queries. That can happen with small customers, with large customers. Maybe they have or they set up some new robotic queries, for example, or like a customers could add like a lot of log queries into a heavily used dashboard, and suddenly, boom, there's a query spike. And when that happened to small customers, like we ended up with these hotspots in the legacy system. And yeah, when this was like too severe, that usually required some manual intervention. Basically, we had to force the system to allocate more resources for a specific customer. And this was not like a very enjoyable experience for us. But yeah, this is quite common.
Okay, let's dive in a bit more on that feature that we've talked about a couple of times already. Was one of the most requested features that Husky was built to solve, which is filtering and aggregating by any field. And Ryan is going to go through this content.
So our goal for solving filtering and aggregation on any field was not only to make sure that you could use all of the fields, but to make sure that the performance was consistent regardless of how many fields that you emitted in your events. We wanted even an unreasonable number of fields that are probably an application bug on the customer side to be okay for Husky. We knew that starting from the data structures was the right way to go here because that's where the limitations in the legacy system came from. So as Guillaume mentioned earlier, our file is split into two locations. The top piece in blue is metadata stored in FoundationDB. And that metadata contains a path to a file in object storage, along with a sparse index of the column names that are stored in that file. And by sparse index, I mean an index where not every column name is present, but one where you could seek to the approximate location where that column would be if it does exist in the dense index. And this metadata is the same size regardless of how many columns that you store in a file. And this keeps the load on the metadata store consistent. The bottom portion in red is the file in object storage. That file contains the dense index of every column name to the beginning byte offset of that column earlier in the file. We store the dense index in the file instead of the metadata store, so that when a customer emits hundreds of thousands of columns, the size of our metadata doesn't change, and we pay for just a bit more space in object storage. The consequence of this is that this index structure requires two I/O operations to seek to the beginning of a column. The first operation will read the dense index, and then there's another I/O operation to seek to the position that we found in the dense index. That's not ideal, given how slow object storage can be sometimes, but thankfully our files are immutable. We use consistent hashing to distribute queries for files to our leaf query nodes, the reader nodes that Guillaume mentioned earlier, so that each node sees queries for the same file potentially many times. This gives us the opportunity to build caches for each individual file, including a cache of the column index. This is one of those things that makes the reader nodes almost stateless. So we cache the lookup of the column name to the file position using a 98% hit rate using a tiny amount of memory. This means we're now back at effectively one I/O to seek to the beginning of the column, which is as good as you can get.
Good. So filtering and aggregating on any field. So we've talked about any field and theoretically as many as the customer needs. But do you have a practical number of columns that you know for sure that Husky is able to support?
We do. So we had a performance issue that we were debugging a while ago, and while we were working on diagnosing it, we came across a customer who had emitted well over 1 million columns in some of their files. And this concerned us because we had never really seen it before. We thought for sure that this was the source of the performance problem. So we spent a lot of time investigating that, and it ended up not being the case at all. It was something completely unrelated, and that well over 1 million columns was completely fine for that customer. We definitely don't encourage that, but 1 million columns is something that it didn't break Husky. So that column index by itself is not good enough to satisfy the goal that we set off at we set off for at the outset, which is not only allowing customers to admit as many fields in their events as they want, but also making sure the performance stays consistent regardless of how many columns they emit. If you're dealing with 1 million columns in a file, most of those columns are going to be sparsely populated. And generating null values for those millions of columns for all the events that don't contain them takes up a ton of CPU time. So we created a sparse encoding for those columns, which only stores the values that are non-null, which eliminates the overhead from all the nulls. So these two tricks, together with a few smaller ones, let us store, as I said, well over 1 million columns in a table without any issues. Now, Guillaume is going to discuss one of those other things that makes the reader nodes almost stateless and is a very important performance optimization for Husky.
So if we look at queries, so there's an example here of a query, and query can usually contain one or multiple predicates to filter data. So here there's an example with 2 predicates, one which is of a specific field, so like service web store in this example, And there can also be predicates, which we call full text search predicates. And that means that they can match against all fields containing textual data. So that's the item created predicate in this example. So some predicates, they are more expensive to execute than others. And in this query, for example, matching the full text search predicate against events is harder than matching the predicates on the service column. So what reader nodes do is that when they run queries in Husky, they track the execution cost of the individual predicates, and they basically cache the matching events for the most expensive predicates. So then when we have like other queries, following queries coming into the system, like this one in example here, if they contain the same like expensive predicate, so here we have the item created predicate, which is found again. Basically, the results for this predicate are now cached, and well, the readers would basically execute the predicate first because the results are there, and only then they would run the new predicates on the filtered data. So it's very common for queries to reuse predicates. And this predicate cache, it dramatically reduces like resource consumptions and in the end, like query execution time. So that was a very important optimization.
Yeah, makes total sense, because usually when you're trying to filter in a lot of logs or events, the first time that you try to filter by some fields and some text, then you realize you're getting too many, and then you start filtering more and more until you get what you need. Good. So when Guillaume was talking about compaction, he mentioned that compaction was important to improve performance, and that is done through the locality. And Ryan is going to give us an idea of what this means and how compaction solves this.
So in Husky, our data layout changes dynamically based on the space and time dimensions. So smaller tables are partitioned into fewer files that cover longer time ranges, and larger tables are partitioned into smaller time ranges. We keep ingestion latency low by emitting tons of tiny files and cleaning them up later for query efficiency. One of the ways that we improve query efficiency is adding data locality to our files, which both reduces the number of files overall at ingestion time and sorts data by some key that is used at query time to improve the number of files that you need to read. On this diagram, time and space are represented by the X and Y axes respectively. As a file gets taller, it covers more of the sort key space, which is the service column here. And as it gets wider, it covers a longer time range. Data locality compactions try to balance the cost of rewriting data with improving the selectivity of the sort key, allowing queries to read fewer files. So for a query that targets just the rows with service C, the purple rectangle overlaps with 7 files. So we'll need to read 7 files to process this query. You can see in orange all of the files that don't overlap with service C, so they'll be skipped. The goal of the data locality compaction is to ideally lay out data such that more of the files are orange in this diagram. So we read fewer files to process the query. This diagram is a very idealized representation of what things would look like at the end of a data locality compaction. They're never this perfect, but it shows that we've created files that are evenly distributed in both space and time. Things are definitely a little more messy than this, but in the end, this is what we're trying to achieve with data locality compaction.
Good. And how are those keys to add data locality based on a key selected? How do you select what key to add locality to?
So our data science team analyzes historical queries for each product type, and they give us some options for what they think the best sort keys would be based on how many files would have been removed if the data set had been sorted by that key, or like ideally, basically. So we look at historical queries to pick the best sort keys, and then we apply that to the products after we've gathered some data.
Okay, good, makes sense. Okay, so before we go to Q&A, again, we have time for live Q&A. So if you have any questions, please drop them on the Q&A button. I see already some questions coming in, so thanks for that. We will cover them in a minute. But before we do that, let's talk briefly about how we are migrating all these products to Husky. Guillaume?
So like a migration is done in basically two big steps. And the first one is to migrate the ingestion. And this one is relatively easy. So we saw that the legacy system consumes events from Kafka. So what we did is just like attach Husky to the same Kafka cluster and consume the same events. So with that, we basically double wrote data for like a few months to ensure that like Husky could keep up with the workload and recover from burst basically as well as the legacy system could. And of course we had to make like some adjustments, but in most cases we were quite happy to see that Husky performed better at recovering from burst than the legacy system. And this was mostly due to its better auto-scaling properties. I mean, when we were seeing bursts, like Husky would like immediately scale the writers and things would go well, basically. And the second step of the migration is to migrate queries, and this is a bit more tricky. So what we did is build a shadowing and comparison system to basically make sure that we had query compatibility between both Husky and the legacy system. So how that works in practice, there is a small percentage of queries which are served by the legacy system that were shadowed to Husky, and then we would basically compare results and make sure that we get the same results on both systems. So this is this is slightly more tricky than it looks because both systems have a different view on the recent data. Like if you consider like the last minute, for example, of data ingested, like both systems, legacy and Husky, they ingest data independently. So like one event could be ingested like in the legacy system first and then come to Husky like a few seconds later, or the other way around. So like basically what we had to do is to for the shadowed query, we had to fork them and rerun them on both systems, basically by shifting the time range, like in the past, and querying past data so as to eliminate basically false positives. And then when we did that, we could effectively like compare results, and this found quite a few bugs that we had to fix. But what we also realized is that the legacy system had some, say, edge cases which we really considered as bugs. But even if we found that the query results were a bit odd sometimes, like in many cases we had to keep the behavior consistent with what the legacy system does, because some of our customers, they relied on this behavior in their monitors. And we know that monitors can wake up people at night. And believe me when I say that, I'm an engineer at Datadog. I know firsthand that monitors can woke you up at night. But in the end, with this shadowing system, that gave us a lot of confidence in the output of Husky, and yeah, we knew that the results from Husky were definitely correct. So the second part of the shadowing was to basically compare performance. So here, we basically shadowed 100% of queries reaching the legacy system to Husky. And we use that to basically measure query latencies in both systems. And what we saw is that Husky has a slightly higher latency floor. And basically, this is because the latency for to access blob storage is higher than the latency to access SSDs in the legacy system. But on the other end, the latency ceiling is much lower than with the legacy system. And that's simply because we can throw a lot more CPUs at a query in parallel. So here, these graphs, basically they show like the maximum latency and the P99 latencies for queries targeting one product at Datadog. And we see that that Husky performs much better in like in both cases. So like with these good results in terms of query correctness and performance, then we just began to migrate queries. And the way we did that was to do it like product by product. So for some products, the migration is complete already. And for others, there's still a bit of work, and that will keep us busy for the next or for the coming months, I would say.
Good. So I guess this all this shadowing was needed, obviously, to be, as you said, to you're confident on query and also performance. But I guess this might be a bit expensive to basically shadow all the ingestion and also all the queries.
Yeah, this is expensive because, yeah, as you said, I mean, it's not only that the traffic is ingested twice, I mean, but queries are also executed twice. So, I mean, normally to be able to migrate to Husky, we have to double write until we have the full retention of our customers' data available on Husky. But for some products, customers can have a very long retention. We're talking more than a year here. And obviously we didn't want to double write for that long. So what we did is implement something to run queries targeting all data on the legacy system, and because the old data is on the legacy system, but new data would reach Husky, and that allows us to basically migrate quickly and not keep the expensive setup for too long.
Good. Okay, so we're ready for Q&A again. You have a Q&A button. Thanks, Guillaume and Ryan. One of the questions actually was if the team was hiring. Yes, all the engineering teams at Datadog mostly are hiring. So if you're interested on joining Guillaume and Ryan or other teams at Datadog, please have a look to our careers page. And please come and send us your CV. Okay, so let's do questions. Let me stop sharing my screen so we can have all your faces here. The first question is about FoundationDB. The question is, what other databases were you considering, and what made you choose just FoundationDB?
I'll answer this one. So we chose FoundationDB primarily because of the performance and reliability that it offers. Our workload for the metadata store is extremely read heavy, and FoundationDB offers exceptional read performance, in my opinion. And the reason that we needed something extremely reliable is that this is there's really no other option than being extremely reliable here. The metadata store is in the critical path of every query that reads data from Husky and writes data to Husky. So we need things to be as reliable as possible. Somewhat for a subtle reason, I think, which is that if we, some people say that I don't agree with this opinion, but some people say that logs data is not that important, and it's okay to drop a little bit of logs. Some logs data is okay to drop every once in a while. And that may be true for some people, but if you're the one operating the system that manages logs, you don't want to be debugging something, guessing whether or not it's your system that lost the logs or the systems that were somewhere else along the way lost the logs. You want to be very confident about your system so that you can diagnose these problems effectively. There were a few other options of databases out there. I think someone could have made a reasonable attempt at using Postgres for this. It would have been much harder. And I think their overall reliability characteristics would have been less. There are also proprietary databases that we could have chosen, but we ended up choosing FoundationDB because it's open source and it meets all of our criteria.
Okay, thanks. The next two questions, actually coming from two different people, are basically the same question. They're asking about predicate cache invalidation. Is it TTL based or you actively invalidating in some way? Similar question came from another person as well.
So it's we don't invalidate the predicates. So basically what you need to understand with predicate caching is that like our files are immutable, okay? And when the cache entry basically correspond to a single file for a single predicate. So if we later run a query which targets the same file, and we have that information, or we executed already like a previous query sharing the same predicate on the same file, we know that the results that we stored, they are correct, okay, because the files did not change. So like what we do is simply like we have a certain number of entries that we allow in the cache. I think that's based on the size that we use. There's probably like some settings regarding the number of entries that we can keep in the cache and the total size of the elements that we keep in the cache. But once the cache is full, we just start to drop like the old ones. So that's like first in, first out. And then if a query come next and target the same predicate than the one we just evicted, then we rerun the predicate. And we realize that it's costly, that maybe it's going to be re-executed again like soon after, and then that's when we take the decision to cache it again. So like elements or predicates which are very or which are run very frequently on the same fragment on the same file, sorry, they tend to be like moved out of the cache and put back in the cache very quickly. But what happens is that most of the time, like users, they run queries over the last, I don't know, last 15 minutes, last hour of data. And so when you keep like cache data about the file, I mean, at some point, this file is not queried anymore, and we can just safely discard the entries that we have in the cache. And that is not a problem anymore because the file is not queried anymore.
Okay, thanks. The next question is, how does one test something like this at scale? Shadow querying can only work once the system is built. So how did you reason about the performance on this before it was built?
Yeah, go ahead, Ryan. I mean,
okay. Yeah, so when we were originally designing Husky, we leaned heavily on the literature from analytics databases, because this is essentially an analytics database. The techniques that we use for processing queries like vectorized execution, columnar storage, and stuff like that, they're pretty much all just state-of-the-art stuff now. There's nothing unknown about them. I'd say you could go find dozens of papers that cover the topics that we had to understand to reason about the performance of Husky before we built it. The only thing I would say that was unknown in the beginning was how we were going to implement full text search in a way that was good enough to meet the quality bar for Datadog, because I think most customers would agree that our full text search is very high quality. So we needed to keep that quality bar up. And that did require some engineering work, but the way that we did that was we just made a first version, which didn't work. We made a second version, which worked a little bit better. And then we have a third version of that now, which is very good, which Guillaume spent a lot of time making good.
Good. As Guillaume, you spend a lot of time making it good. Do you want to add anything to that?
Yeah, I don't really want to talk about specifically about full text search. I mean, but for this question, I think I mean there was indeed a lot of unknown when we started this project. But I mean, there are many different products at Datadog, and we did not like target the whole suite of products from the beginning. So we started like small and like experimented a lot, like ingesting like all the data for one product, and then like experimenting with queries, see how big our reader pool should be. And at the beginning, like things would not like auto scales, and this was added basically along the way. So it was like going step by step until we were satisfied with the performance for one product, and then the second product, and then the third product. And at some point, I mean, you start to really understand how the system works and how it performs, and which type of queries it's good at, and on which part you should work, because you know that's where you're dealing with like some like performance problems, for example. So that was kind of like very natural once the project was started, and once we started to implement products. It was not very difficult to basically get a sense of the size of the system that we should set up to be able to support a new product.
Good. Okay, thanks. We don't have any more questions from the audience, so and it's almost at time, so we are going to leave it there. Thanks a lot, Ryan and Guillaume, for participating and sharing this cool project, which is Husky. Thanks the audience for coming in live and ask those questions. That makes these episodes a lot more interesting. And again, just letting you know, this is being recorded. So if you thought this session was interesting for a colleague or a friend, it's going to be published very soon on our website, datadoghq.com. So feel free to share it with your peers.